ask yourself, when are they isomorphic? Where isomorphism, here let's abbreviate this with a strict x and a strict y. And we say that x is isomorphic or conjugate to y if there's a mapping theta from x to y, which has the property that if you first apply t and then theta, it's the same as first applying theta and then s. T of theta of mu is equal to mu, and theta is invertible. Theta inverse maps x to y, measurable of course. So theta inverse of c is equal to b, and theta of b is equal to c. So this is the double inverse. So the question is, when is this the case? This is, as I say, a classic problem. Some of the early progress or early history I spoke about 40 years ago in a talk on the isomorphism problem in ergodic theory at a meeting of the AMS. Many things happened in the intervening 40 years. I can't record all of that. I'm going to focus on two new developments of the 21st century. One of them concerns the problem in this classic setting, and the other concerns the problem in a more generalized setting, which is closer in spirit to a lot of the work that you're going to hear about. Namely, in this setting, the dynamics is the dynamics of the group Z, which is represents the iterates of T. In more abstract dynamical systems and ergodic theory, one replaces Z by a more general group. How general? Well, let's talk about an arbitrary countable group. So if G is a countable group, we can pose the same question where you replace the single transformation by a representation of the group as measure-preserving transformations. So everything remains the same except that now the T is indexed by the group elements, G. And this is a representation of the group in the sense that T, G, TH, this composition is T, G, H. Well, it's exactly the same when you talk about the isomorphism problem or classifying measure-preserving actions. Now, the first reduction is, or reduction or specialization, is to restrict attention to ergodic actions. So the definition of ergodicity is surely well known, but I record it anyway. So we'll talk about ergodic actions. So the action is ergodic if the only invariant function, so f of tx equals f of x, mu almost everywhere, if and only if f is equal to a constant. So for ergodic actions, the general problem of isomorphism has proven to be very difficult. One special class of transformations, which are really the basic examples, especially in this general setting. If you talk about a general group, the first question students ask you is, what is an example of such an ergodic action of a countable group? And for interesting actions, we would like them to be free. So I'll just mention one more definition, which is, again, not so relevant in the case of Z, but a free action, this simply means that the measure of the set of fixed points is equal to 0 for all g which are not the identity. So, if somebody asks you, give me an example of a free ergodic action of a countable group, the basic example of what are called Bernoulli actions this is a generalization of IID sequences coming from probability theory. And this is simply the following. You start with a finite probability space, so P is just a probability distribution. I say finite, but this can of course be countable or just an arbitrary probability space. And then you take the possible values that the random variable takes. You take the set A, which is 1 up to little a, and you consider the space A to the G. We call this omega. This is the space of sequences indexed by G. On this space, the group acts. The group acts with what is called the shift. So if you take a point, omega, in this product space, and you take an element of the group G, and you act on omega by sigma G, the shift indexed by G, you have to evaluate it to tell what this function is. You need to know what it is for an arbitrary h, and you take this to equal omega hg. I multiply on the right. If I would multiply on the left, I would have to put in an inverse in order that an honest representation. The TGTH rule would not work unless I put in an inverse. But for the right action, you can just multiply this. Now, so far, this is just a space, but of course, this has a topology. It's a product space, a compact space. It's a Cantor set. It has a Borel sigma algebra. And we put a measure on it by taking the product measure. We take this probability measure and raise it to the G power. This is now a probability measure mu on this space omega. This shift preserves the measure. And this is called the Bernoulli action. So for general groups, you can ask the question, when are two such Bernoulli actions isomorphic? By the way, the original time I was supposed to end was 11:50. What is the new time?
The duration will be the same.
Excuse me?
Duration will be the same, 55 minutes.
Yeah, I forgot what time I started. So when did I finish?
Until 12:15.
12:50. Okay, thank you. Okay, so I've defined the Bernoulli shift. Is this clear? And I've defined it in the context of a general group. Of course, a special case is just the same indexed by Z. Now, for Z, the isomorphism problem, the problem of classifying Bernoulli shifts, is an old problem, and it was solved in 2 steps in the years 1958 and 1969. And the main figures here are Vadodara and Ornstein. And what they proved is the following. So, Kolmogorov if, and I'll abbreviate things as follows, P to the Z, this is an abbreviation for the triple A to the Z, B, the Borel sigma field, the measure, and the shift. If P to the Z is isomorphic to Q to the Z, then H of P equals H of Q, where this is equal to minus the sum of Qj log Qj. So this is the entropy or the information of the basic random variable. And Kolmogorov proved this by defining an invariant which we call the entropy of such a system. So Kolmogorov defined something called the entropy of X, which is defined using this basic quantity. I'm not going to write down the definition, I just to say entropy of X. This is very familiar to students. It's one of the first things that they learn in ergodic theory. I won't go into the details. So this was in 1958, and a little over 10 years later, Ornstein proved the converse. If H of P equals H of Q, then P to the Z is isomorphic. So this is an old story. And I'm supposed to be telling you about recent trends. Recent progress. So the recent progress has to do with the generalizations of this theorem to more general groups. So in order to describe this, I have to talk about classes of groups. So the class of groups that were for which a great deal of the classical ergodic theory was extended was the class of amenable groups. So amenable groups include abelian groups, abelian solvable, locally finite. These are increasing unions of finite groups. It's easy to give a definition. Maybe lights are blinding me because I find it hard to see the audience. So allow me to go in the dark so that I can see you. Now, who needs a definition of what is an amenable group? Please raise your hand. Don't be. Oh, good. So what is an amenable group? It's a group that has so here's a definition. G is amenable if there exists Fn finite sets in the group in G such that, I'm not sure you can read this down below, so here's the defining property. For all G in G, if you multiply Fn by G and take the symmetric difference with Fn, so that's, here's Fn, and then there's GFn, and the symmetric difference is the part that's in one but not in the other. that shaded part, and you compare the number of elements to the number of elements in Fn, well, I've given two notations for the number of elements, both the absolute value and number, but it's just the number of elements in this set divided by, these are finite sets. This goes to 0 as and the example you should think of is for z, you can just take 0 up to n. For z to the d, you can take all u in the integer lattice such that the norm is less than or equal to n. All kinds of things like this will work. These are all amenable groups. So an amenable group is a group for which you have such a sequence. And this is the class for which the ergodic theorem of von Neumann is easily generalized. Other ergodic theorems can be proven, and so on. And the theorems of Kolmogorov and Ornstein were generalized to amenable groups quite some years ago in a couple of papers by Ornstein and myself. What is a group that's not amenable? In order to understand the concept, you have to understand not only what it is, but what it isn't. So what is a non-amenable group? So not amenable the basic example is F2. This is the group generated by A, B, A inverse, and B. This is the free group. I say 2, but any number of generators on 2 or more generators. Now, you can still ask about the isomorphism theorem for Bernoulli shifts. Classify Bernoulli shifts over the free group. And actually, we asked that question. And then we found a simple example, which I'll describe very briefly. Give you something to think about. Before I give the example, I should make one further definition. I spoke about isomorphism. There's a more general notion, which is called a factor or an extension. So X is an extension of Y. Remember, these are four tuples. Is an extension of Y, or Y is a factor. Y is a factor of X. If there exists a measurable mapping from X to Y, which takes the measure mu to the measure mu, you remember that X represented a system where mu was the invariant measure, here mu is the invariant measure. Theta is measurable. Theta inverse of C is equal to B. It is contained in B, but it's a proper sigma algebra in general, sub-sigma algebra. It's not inverted. Theta not necessarily inverted. And actually what Kolmogorov proved in 1958 was not only that if Bernoulli shifts are isomorphic, they have the same entropy. Kolmogorov's theorem gave much more. It said that if there exists a theta from P to the Z to Q to the Z, then the entropy of Q is at most equal to the entropy of Q. So a factor map reduces the amount of information. It can't increase the information. This is a very intuitive theorem. It's certainly true at the level of random variables. It's a classic observation that if you have a map from one random variable to another, if one random variable is a function of the other, the information in it is at most the information in the original random variable. This is just an extension of this to the dynamic entropy that Kolmogorov includes. And this theorem is sort of much easier to prove than Ornstein's isomorphism theorem. And the first thing we tried to ask ourselves is this kind of theorem true if you replace Z not by an amenable group, there we could prove it, but by the free group. And then we came up with a simple example, which I can describe to you. Okay. Which does the following. So there exists a factor map theta from the 1/2 Bernoulli shift over the free group on two generators to the 1/4. This is called the two shift. This is called the 4 shift for obvious reasons. The basic entropy here is, of course, log 4. H of a quarter is log 4. Here it's log 2. We've increased the entropy by a factor. This example, which I'm going to describe in a second, sort of convinced us that you can't develop an entropy theory for the free group on two generators. And how does the example go? You do the following. You represent the symbols here by so you take for the space of the two shift -1 plus 1 to the F2. And we want to define a mapping from this space, which I'll call omega 2, to the space of pairs. So ±1 plus -1 to the F2. So I'm given a configuration here. I'm given an omega here. And I want to define theta of omega. To define theta of omega, I have to tell you what it is at each point. Well, let me tell you what it is at the identity element. To compute theta of omega at the identity element, you look at omega at the identity element and omega at A, and you look at omega at the identity element and omega at B. The free group, I remind you, is generated by A and B, A inverse and B. With a proof of the fact that theorem for F2 if P to the F2 is isomorphic to Q to the F2, then the entropy of P what Bowen did is he defined an invariant, what he called the F invariant. It's based on an entropy computation. I'm not going to give you the definition. He defined an invariant, showed that it is an invariant, and he computed it for the Bernoulli shifts, and it turned out that if they were isomorphic, they would have to have the same. His explanation of this is also given in terms of the F invariant. This map that we've defined is actually a 2-to-1 map. And the increase in entropy comes from the fact that when the free group acts on a finite space, the value of the F invariant is negative. Something quite unintuitive, but it gives an explanation of our example, and it proves the analog of Kolmogorov's theorem. Now, this was remarkable enough from my point of view. Less than a year later, I got from him, I should say, by the way, that when I first got this preprint from Lewis, I hadn't known it yet. And I got this paper which claimed this theorem, and I said, this can't be right. So unlike what I usually do when I get papers like this, I sat down and I had to read it very carefully because I was looking for a mistake that I was sure was there. But to my surprise, there was no mistake that couldn't be easily fixed, and that theorem was right. And now comes this really remarkable theorem, which is the same statement, not only for the free group, but for a much larger class of groups. This is Bowen's second theorem, so this is Lewis-Bowen theorem 1. Now comes theorem 2. If G is a Sophic group and P to the G is isomorphic to Q to the G, Q to the G, then H of P now I'm not going to ask for hand raising as to who does not know what a Sophic group is. I'm not going to give you a formal definition. Don't quite have the time for that. I'm just going to draw you a picture of groups. So here are amenable groups. Here are Sophic groups. Here is a class that is certainly familiar to many people in the audience. These are the residually finite. Residually finite are regular people. Residually finite. So these are groups for which you have Hn, an increasing sequence of normal, decreasing sequence of normal subgroups which decrease to the identity, each of them a finite integral. So these are groups that you can separate the elements of the group by homomorphisms from the group into finite groups. So all linear groups, finitely generated linear groups, are residually finite. Of course, not all amenable groups are residually finite, because, for example, a free group on any number of generators is residually finite, but not free. They're not amenable. Sophic groups is some common generalization of this, and it's a subclass of groups, but nobody has proven that some group is in this intermediate range. So this intermediate range between Sophic and whole groups is, it's unlikely that it's empty. I mean, if it would be empty, I wouldn't have to define Sophic at all. So that's one of my excuses for not defining this. It's conceivable that there's no proof it's not Sophic, although unlikely. In any event, Bowen has extended Komodorov's theorem to all Sophic groups. More recently, he extended Ornstein's theorem. This is another beautiful achievements which I can explain to you, but I want to spend the remaining part of my talk on another line of recent developments on the isomorphism theory. And since I can't go into a great deal of detail in the space of one talk, I do want to mention another line of recent developments, which is quite separate from the line that I've been discussing up to now. So up to now, I've been focusing somehow on the good news, namely the Bernoulli shifts where there has been a lot of success, not only in the classic example, but even almost all groups. However, if we go back to Z, so I'm beginning the last part of the talk, and if you sort of lost me in all of these abstract groups, we can come back down to earth again. I'll return to talking about the classic situation of a single transform. And while entropy classifies things like the Bernoulli shifts and many other examples, in fact, the first work of Dani that I became familiar with was work of his showing that certain homogeneous flows are isomorphic to Bernoulli shifts. So a lot is known in a positive direction, but the search over the last 40 or more years, or 50 years, for further invariance and more understanding of when our ergodic measure preserving systems isomorphic has been very elusive. And some of the recent progress that I want to tell you about has to do with an understanding from our point of view of why the problem is hard. So, the Greeks tried to figure out what is the length of the hypotenuse of the length of the diagonal of a square, and they couldn't compute it. They measured it, they tried to measure it more and more accurately, and they finally came to the realization that it was irrational and that you couldn't really express it as a ratio of two numbers. This was, I think, one of the really milestones in the development of mathematics, understanding that some things are impossible. And in some sense, this is the kind of progress we've made on the isomorphism problem. We've understood why it's so difficult. Let me describe that. It's slightly technical, but I try to at least explain what the statement is. So when you can't understand something better, you ask yourself, what about the question as a whole? So for that, you define the relation. So let's define, and we might as well be talking about ergodic transformations of the unit interval. So x will now be the unit interval with Lebesgue measure. All standard measure spaces, all of the measure spaces I've been talking about are equivalent to the Lebesgue measure in the unit interval. And let's define the conjugacy relation or isomorphism relation. I'll call it I. It's a subset of E NPT cross NPT. So what are these acronyms? ENPT are the ergodic measure preserving transformations, measurable and measure preserving. So this is the vague measure preserving transformations of the unit. So the measure preserving transformations form a nice group. They're a Polish group. The ergodic ones are a generic set, so this is a Polish space. This has the structure of a complete separable metric space. And we define the relation I. I consists of all the pairs T and S such that T is isomorphic to S, and what that means is that there exists an R in NPT, not ENPT, but NPT, such that R, T, R inverse is equal to. This is why it's called a conjugacy relation. T and S are conjugate elements in the group of measure preserving transformations. Now, the global perspective asks the question, what is the nature of this set? So this set is, from its definition, expressed as the projection of a very nice set, not in this space, but if you add one more coordinate. So if you look at the space of triples, TSI as an element of the ergodic measure preserving transformations, plus the ergodic measure preserving transformations, plus the measure preserving transformations, such that you look at this collection such that that equation is true. Such that R, T, R inverse is equal to. Here's where the graph is. So in this space, this is a closed set. It's a very nice set. Just writing one equation in these variables. And I is the projection. Just forget R. Now, projections of closed sets in Polish spaces, you might think they're nice sets. You might think, for example, that they're Borel measure. If you do, you're going in the footsteps of a great mathematician, because that's what Lebesgue did. This is Lebesgue's famous mistake, where he thought that the projection of Borel sets in Euclidean space are Borel measure. But it was discovered by Suslin and then developed by Lucene that these are not measurable. These are what are called analytics. is analytic set. This is the definition, the projection of the closed set. It is analytic. And the problem was, is it Borel? Is it Borel measurable? Being Borel measurable would mean that while you can't define invariance, there would be some kind of countable protocol, some countable sequence of questions which, when presented with T and S, you could decide are they isomorphic or not. Entropy is an invariant which you need only inspect T and S individually. The question for the pairs is there some way of, given a pair, can you effectively decide, are they isomorphic? And this amounts to the question of, is this a Borel set, or is it analytic, but not Borel? What we discovered a number of years ago, and the we now is Matt Foreman and Dan Rudolph, tragically passed away a couple of years ago, and myself. So what we discovered is something even stronger than this relation. What we discovered is the following. The set of T in En such that T is conjugate to T inverse is a complete analytic. In particular, not Borel. Complete means, in some sense, that it's the most complicated kind of analytic set that there is. Maybe I've burdened you with enough sort of abstract concepts, and I won't give you a formal definition of what a complete analytic set is. I will give you a hint as to how we prove this theorem by indicating sort of what it is that we actually do without, of course, giving you any of the details. So instead of giving you a definition of what a complete analytic set is, I'll give you an example. The example consists of the following. T is the space of countably branching trees. So these are trees with a root with possibly a countable number of successors. Each vertex has possibly a countable number, but some things may have. All possible such objects. It's easy to put a topology on this, turns this into a Polish space. This is a nice, complete separated matrix. Then there's a subset, T infinity. This is those trees that have an infinite range. Unlike finitely branching trees, just knowing that a countably branching tree is infinite doesn't mean that there's a branch which actually runs off to infinity. And this subset is easily seen to be analytic, but it's a complete analytic set. T infinity is a complete analytic. So it's an analytic set which is not Borel measured. This set is not Borel measured. That's another exercise you might try. And what we do is we give a construction, we give a mapping. So we define, with this I conclude, a map, which is actually continuous from T to ENPT, mapping the whole tau such that such that pi of tau is isomorphic to pi of tau inverse if and only if tau belongs to T. Yeah. What? Yeah, no, I understand. One of these concepts. So this continuous map gives a reduction of the set of trees that have an infinite branch to the relation of isomorphism, because you can decide whether or not a tree has an infinite branch by computing the associated ergodic measure-preserving transformation and asking, is it isomorphic to its inverse or not? So the classic fact that this is a complete analytic set, together with this construction, shows that the isomorphism relation is a complete analytic set. And what that means is that in some sense, in some rigorous sense, the isomorphism problem is difficult. It gives some explanation as to why we have had so much trouble in finding more invariants beyond entropy. I have more explanations of this that run off in different directions, and I have sort of more reasons for ways of convincing that the isomorphism problem is hard, but I think I'll stop here and leave some time for questions. Thank you.
Thank you very much, Professor Weiss, for a very illuminating talk on the isomorphism problem. We have time for a couple of questions.
Yeah. So would it be totally inaccurate to say that one interpretation of this is you'd need sort of an infinite list, an uncountable list of invariants to distinguish for the general?
What you need is some kind of uncountable protocol, some uncountable method for deciding.
Right. It might not be a list of numerical
Right.
invariants. It might be.
No, a list of numerical invariants can be combined into one.
Sure.
I mean, Polish spaces allow you to take countable products.
Right.
But uncountable lists, that's another story.
Any other questions?
Just curious, the Sophic group
Yes.
terminology, is it just a finiteness somehow, or does it actually have something to do with Sophic shifts?
No. It has nothing to do with suffix shifts, except that I recycled the name, taking it from, I originally put it in as a generalization of shifts of finite type, and then Gromov introduced a class of groups that he called, in his paper, it was essentially this class, but his terminology was groups with an initially subamenable relation, some string of terms which were very difficult for me to digest, as was the way he defined his presentation, and so I wrote a short paper in which I gave it's a generalization of finiteness, it's a finiteness condition. And then I just took the name again. I didn't think that this would catch on. It has. And actually, there is a relation. I mean, the first thing that Gromov proved for Sophic groups was a theorem from symbolic dynamics. It was the surjunctivity of Gottschalk, which is a property of symbolic dynamical systems over a group. I mean, I don't have the time to give the whole story. But you can find this explained all, like there's a Tullio Ceccherini, Silverstein, and Cournaire. And Cournaire have written a lovely textbook on cellular automata over groups, in which they have a long chapter on the Sophic groups and on the symbolic dynamics over the Sophic.
Any other questions? I don't see any hands raised. Next, thank Professor Weiss once again for the. And then talk to Professor Weiss.